When pumping a bore well, Darcy's law applies radially, drawing the water table down into a V-shaped cone of depression. Zooming into the pores, total porosity splits. Specific yield freely drains, while specific retention stays bound. This requires laminar flow, with Reynolds number below 1. Pinning down these physical constraints and soil properties first gives you a clear mental model. When you face a dense AEE word problem, knowing the physical behavior of the aquifer keeps you grounded before you even touch a calculator. This diagram compares Thiem's equations for steady radial flow side by side. We have two distinct formulas depending on whether you are working with an unconfined aquifer or a confined one. Notice the difference in the head terms. The unconfined equation uses squared terms because the actual area of flow shrinks as the water table drops. The confined equation uses linear terms because the aquifer thickness is fixed between impermeable layers. Next, look at the denominator. Examiners test your notation here. The natural log of R over RW is mathematically identical to 2.303 times the base 10 log of R over RW. Pick one format for your notes and stick to it so you avoid doubling up on conversion factors. Finally, pay attention to the well dimensions given in the prompt. Test questions frequently give you the well diameter. These formulas strictly require the radius, RW. If you see diameter in the question, strike it out and divide by 2 immediately. Missing the squared terms, missing up your log bases, or plugging in the diameter will throw off your final calculation. Rigorous attention to formula notation secures these points. This diagram illustrates an open well recuperation test. First, you rapidly pump the water level down to an initial depression head, S1. Then, you stop pumping and let the water naturally seep back in, rising to a new level, S2, over a measured time period, T. We calculate the specific yield of the well using this equation. Pay close attention to the terms C over A. Because the log ratio is dimensionless, the resulting unit for this specific capacity per unit area is simply inverse time, like 1 over hours. Let's test this. An open well is depressed to a head of 4 meters. After 2 hours, it recuperates to a head of 2 meters. Pause the video now and calculate the specific capacity per unit area. Let's walk through the math. Plug in the time of 2 hours, apply the 2.303 multiplier for the base 10 log, and set the head ratio to 4 over 2. The log of 2 is roughly 0.301, giving us a final answer of 0.346 inverse hours. The recuperation test is one of the most frequently tested time-based scenarios in AEE hydrology. Executing this calculation sequence accurately guarantees you a quick, reliable score. The total drawdown in a pumping well, SW, comes from 2 physical causes. The first term, C1Q, is formation loss, the linear resistance as water travels through the soil. The second term, C2Q squared, is well loss, the nonlinear resistance caused by turbulence as water forces its way through the well screen. If we divide the discharge rate, Q, by that total drawdown, SW, we get the well's specific capacity. Notice the dimensions, length squared over time. Because of that squared well loss term, a well's specific capacity actually decreases as you pump water out faster. Maps out the log conversion rules and highlights the dimensional differences between specific yield, specific capacity, and the recuperation constant. Dominating the AEE exam requires pairing formula memorization with a sharp eye for dimensional inconsistencies and mathematical traps. When you maintain strict unit hygiene and respect the log rules, you stay in total control of the numerical solution.